Hello again, this is Galen Pickett, Cal State University of Long Beach, Physics 151. Today I want to talk about sections Chapter 3.10 and Chapter 2, Section 4. This is about the iterative determination of motion and what does mechanical determinism have to do with what we've been doing with momentum principle. So the basic question is this: given the position of an object, where it starts off, and where it's headed, where it is, what its velocity is, and if you're given what the force is as a function of time, is that sufficient to predict where is the object at any other time? So let's take a very simple case. So here's an object, it has a mass m, here's my origin, so there is r initial, and let's say that that is what v initial times delta t is, this little vector here that would take me. Now let's assume first that the force is equal to 0. If the force is equal to 0, if I wait, so there's my initial time, this is basically repeated applications of position update. So this is one of the conditions we've got. It's a special case, but I know where it starts off, I know where it's going, and I know what the forces are. In this case, it's 0. So if I wait, so there it is, t is equal to 0. If I let t is equal to delta t, I know exactly where the particle is going to wind up. It's going to wind up where the velocity times the delta time would take it. And now I could use this as the new initial, and then go ahead in time another delta t. So when t is equal to 2 delta t, where am I going to wind up? Well, that is the velocity times the time. I would do exactly that same thing over again. Take that the velocity didn't change because the force is still 0. So I'd wind up exactly that. That would be at t is equal to 2 delta t, 3 delta t. It's the same no interaction path of particles that you would see back in chapter 1. So now let's change what's going on. Now we can make the force be anything we want, but let's have the force. I want the force to point in that direction, and it's got a constant magnitude and direction. So now, using position update is not going to be sufficient. We're also going to need momentum principle, and probably the momentum update version of that. So let's see what that looks like. So again, I've got a particle that starts here. So there is what my r initial is. And let's say that is my v initial. So if there were no force at all, I would wind up exactly here. But there is a force. So what does momentum principle say? M times v final is equal to m times v initial plus the force times delta t. So that's exactly the position update form of momentum principle. If I divide everything here by m, I get that the final velocity is equal to the initial velocity plus f delta t over m. And this is a constant vector. If that's what the force is, I'm going to let this little red vector be f delta t over m. That is how much the velocity will change by. So here is what my initial statement for what the initial velocity is going to be. But the final velocity is going to be changed because of this vector. So instead of the particle winding up here, it has to wind up here. So that is my new estimate for what the velocity of the particle is. And now this is my new initial. So if the force turns off, this little blue arrow would tell me where the particle would wind up, right there. But it's not, because this force is changing the velocity. So I add to that this little force here, and that is where the particle actually winds up. So there is the actual final velocity that we wind up using. Again, now I use this one as the initial one. That's where I would wind up. but I don't wind up there, I wind up somewhere below, because I have to take this little red vector added. And that is now. So the actual trajectory, instead of being this straight line, is exactly this parabolic trajectory that you get from using momentum principle, average velocity, and position update, this chain of reasoning. So the way this would work, we're given the initial and R initial. We'll let V final equal the initial plus F delta T divided by M. And then we'll let R final equal R initial plus delta T times that V final. This is a way to take the initial velocities and get the final velocities and positions, and then we just keep doing that. We just run this cycle as often as we want. If the force changed in time, that's where we put in. We put in different red arrows from one time to the next. But if the force is a constant, we've got that all laid out. So what this means is, this is something that gave people in the 19th century, so the 1800s, a lot of philosophical problems. If you knew R initial for everything, so you knew where every atom was at some particular time, and you knew what the velocities for everything, there would be no freedom left. No freedom left. The entire universe is going to run forward because of the momentum principle and the position update principle. There's no room left for free will, anything like that. It's just a mechanism that runs forward in time. Now, that is still, I think, a philosophical problem that people need to deal with, but it's become a feature in many video games that you, I'm sure, have played at one time or another. Here is one. So, the angry bird, the initial position of the bird is given by the game. It's where this slingshot is. The only thing that you can give the bird is different initial velocities. So I'm going to give my bird a velocity like so, and from that time forward, there's nothing else that I do to control the bird. Everything else is being run by the position update, and boom. So you see, even the dots here are showing you what the trajectory looks like from one time to the next to the next.